Hi folks. Now that we've learned the basics of balancing chemical equations, we need to look at the different types of reaction that exist. And this is going to allow us to start making predictions about what products we will form when we react chemicals together. Of course, this is super important in science. You couldn't make anything if we weren't able to make predictions about what chemicals are produced when you mix two chemicals together. So the first kind of reaction that we're going to look at is called a synthesis reaction. Sometimes it's called a composition reaction, but I will always call it synthesis. A synthesis reaction is any reaction that has just one product, You're going to have two or more reactants. Those reactants are often elements, but they don't have to be. And so the general form is represented by this diagram. You've got one substance on its own plus one substance on its own, and then they come together to form a single substance. So one example of this would be forming hydrogen chloride gas from the separate gases, hydrogen gas and chlorine gas. So an element plus an element, in this case, are reacting to form hydrogen chloride. These don't have to be elements, but in examples where I ask you to predict the product, those will in fact be elements. There are more complicated synthesis examples out there, but those are not the ones that I will ask you to predict the products for. Okay, so we know what a synthesis reaction is. Synthesis just means to make something. We're making a single compound. How do we predict products if we're just given half of a chemical equation? If the reactants are two elements, and I'm asking you to predict the products in Chem 1, then you can be sure that it's a synthesis reaction. You would use the common ion charges, the oxidation states, to predict the one product that the substances will form. So here in this example, if I start with magnesium and nitrogen gas, then how would these two elements combine together in a formula? Well, looking on the periodic table, magnesium has a charge of +2 and nitrogen has a charge of -3 in its compounds. So how would those two ions come together? I would need 3 magnesiums for every 2 nitride ions. And so these would react to form magnesium nitride. Now, I don't just stop there. I need to make sure that this is actually balanced. I seem to have the right number of nitrogens on the left side and the right side, but I don't have the correct number of magnesiums. I've got 3 on the left and just 1 on the right. But fortunately, this is easy to balance. I just need to write a 3 in front of the magnesium on the left side, and I'm all set. With calcium reacting with chlorine, calcium, I see that we've got an element and an element, so I think, okay, this is a synthesis reaction. Calcium forms ions with a charge of +2. Chlorine forms ions with a charge of -1. How do those come together? CaCl2 is the correct formula for calcium chloride. And this is in fact already balanced as it stands. There's 1 calcium on each side and 2 chlorines on each side. So we're all set. Decomposition reactions are the next kind of reaction that I want to talk about. Decomposition reactions are like the opposite of synthesis. Instead of making something, we're taking one thing and breaking it down. So any reaction that just starts with one reactant is definitely a decomposition reaction. You can form 2 or more products. Anything that I ask you to predict will only have 2 products, but you can have more complicated decomposition reactions. The general form is AB, where you've got 2 different elements bonded together, and then you break them apart so that you just have element A and then element B. A standard example of this would be the decomposition of water into its component gases, hydrogen gas and oxygen gas. And this is the process by which you make rocket fuel. You need the hydrogen gas for that. So, how do you go about predicting the products? Again, there are complicated decomposition reactions out there, but if I'm asking you to predict the products, it's going to be one of the easier examples. So, anytime you see just one reactant, it is a decomposition reaction. So here, there's just one compound to the left of the arrow. If the reactant is a compound made up of just two elements, like we have here, sodium and chlorine, then it's a binary compound, and therefore the products are just going to be the elements that were in the compound. So sodium, when it's not an ion, is just sodium metal. And chlorine, when it's not an ion, is a diatomic gas. This is why I said knowing those 7 diatomic elements is so important. You need to recognize when you see chlorine and you're trying to make it into an element that it needs to be diatomic. This is not currently balanced. It's balanced for sodium, but not for chlorine. And if I write a 2 over here, then I need to write a 2 in front of this sodium as well. We started with 1 sodium on each side, but unbalanced chlorines. So we had to do this. Yes, our numbers do match up. Calcium oxide. The elements making up calcium oxide are calcium and oxygen. Remember, whenever you see a capital letter, that's the start of a new element. Calcium is a solid metal. Oxygen is a diatomic element. It's a gas. And therefore, in order to balance this, we need some coefficients, as you see here. So that's a decomposition reaction. The next kind of reaction that we're going to talk about is called a single replacement reaction. This is when you have one element replacing another in a compound. So in a single replacement reaction, your reactants are going to be element plus compound, and your products are going to be element plus compound. But it's not going to be the same element plus compound that you started with. You're going to change things up a bit. So if we look at what this form looks like, here I have an element, one element by itself, and I have a compound. And then what happens is the A takes the place of B and boots B out so that B is all by itself. And so I'm representing this here with the colored dots so that you can see that yellow was bonded to red, and then blue kicked the yellow out of the way, and now blue is bonded to red. Okay. I really enjoy thinking about, jealous boyfriends and girlfriends when I do these reactions. So whatever helps you remember single replacement, just one person gets replaced. Here's an example. Copper is a more reactive metal than silver. So when you have metallic copper and a silver compound, copper will take the place of that silver in its compound and boot silver out so that silver is all by itself. And copper takes the place of the silver ion in the compound. So, how do we go about predicting the products of a single replacement reaction? Generally, if you see that the reactants are an element plus a compound, and I'm asking you to predict the products, then it is a single replacement reaction. Now, there is an exception to that we're going to look at in a couple slides from now. Combustion reactions could also fall under the category of being element plus compound. So we'll look at that in a moment. But generally speaking, element plus compound, you should think single replacement. If the reacting element is a metal, it's going to take the place of the cation in the compound. That positively charged ion is going to be replaced by the metal. The old cation, whether it's metal or hydrogen, becomes the new element. So metal is going to replace metal, or metal is going to replace hydrogen in a single replacement reaction. What if your element isn't a metal? What if it's a nonmetal? The nonmetal is not going to take the place of a metal. Like is going to replace like. The nonmetal is going to form an anion with a negative charge, so it has to take the place of the negatively charged ion in the compound. The old anion, the nonmetal, is going to become the new element. So let me show you what I mean by this. Let's go back to this example again. The metal here took the place of the metal. It did not take the place of the anion. That's because you can't have copper, when it forms ions with a charge of +1 or +2. In this example, it was +2. And silver also forms positively charged ions. Those positively charged ions repel each other. They can't come together because they have both have positive charges, so they don't attract each other. Instead, the positively charged ion is going to be attracted to this negatively charged nitrate ion. Okay, we're still going to be using the common charges to predict the correct formula for the compound. So let's look at what we've got here. Aluminum is a metal, so it's going to take the place of the cation in this compound. This compound has copper ions with a +2 charge and chloride ions with a -1 charge. Aluminum is going to stop being an element and become an ion, and it's going to have a charge of +3. So it's going to boot away the copper and get rid of it and pair up with the chloride. Opposite charges attract. So aluminum with the chlorine or the chloride ion, +3, -1. The formula is going to be aluminum with 3 chloride ions. The copper cannot disappear. The copper is still there, but it becomes just solid copper. It doesn't have a charge anymore. This equation is not balanced, so we need to look at balancing it. We need to have 2 aluminums, 2 out front so that I can have 6 chloride ions, 3 out front here so that I can have 6 chloride ions. Now I need to make my aluminums and coppers balance. I need a 2 in front of the aluminum and a 3 in front of the copper. In this example, my element is a nonmetal. Because it's a nonmetal, it's going to take the place of the nonmetal in the compound, not the potassium. And again, this is because fluorine is going to form ions with a charge of -1. Potassium is +1, chloride is -1. The negative is going to be attracted to the positive, not the negative. So we boot the negative away, kick that one to the curb, and we are left with potassium fluoride plus the element chlorine. Now, remember, chlorine is diatomic, so it needs a subscript next to it. And it's not quite balanced. We need a 2 in front of the potassium chloride so that we can have 2 chlorines, and therefore we need to have a 2 in front of the potassium fluoride. And this is a correctly balanced single replacement equation. Next, we have double replacement. So if single replacement was about like some weird love triangle, this is like a love square or something like this. So in a double replacement reaction, ions in 2 compounds change partners. The reactants are compound plus compound, and the products are compound plus compound. It is actually possible in a double replacement reaction to have more than 2 compounds at the end, because sometimes there are kind of further reactions. The general form is AB plus CD makes AD plus CB. So notice that like the B and the D switch places. I kept the A where it was. I kept the C where it was, but I decided to trade places with the anions, the negatively charged ions. Again, there's a picture representation of what that looks like. One real-world example of a double replacement reaction is this one here. Lead 2 with nitrate ions and potassium with chromate ions. In this example, you can see that the positive ion is attracted to the negative ion, and that's why we have lead 2 chromate as one product. And the positive ion is attracted to the other negative ion that it wasn't attracted to before. And therefore we get potassium nitrate as the other product. Just make sure that you do always write the cation first. So the correct formula is KNO3. Don't write the NO3 first just because it looks like it came first in the reaction. So how do you predict the products of a double replacement reaction? First of all, you need to identify that it's a double replacement reaction. If I give you an equation where you have to predict the products where the reactants are a compound plus a compound, then you know it's a double replacement reaction. I think the best approach is probably to just switch the places of cation 1 and cation 2. If you always do that, then you should be in a good position. If you prefer, you can switch the anions, but just pick one system and stick with it once you find something that works for you. Again, we're going to use the common charges to predict the correct formulas for the compounds. So let's look at some examples here. I have a compound and I have a compound. So I should automatically think double replacement. Silver is a metal, so it forms cations. The nitrate ion is an anion. Sodium is a metal, so it forms cations. Chloride is a nonmetal, so it forms anions. So my positive charge was attracted to this negative charge. It needs to find a new negative charge. It wants a new partner. So we'll pair them up that way and write silver chloride. Positive 1, negative 1. This is the correct charge. And then these two go together. The sodium positive charge with the nitrate negative charge. NaNO3. Positive comes first. So this is actually already balanced. And so this is a correctly balanced double replacement reaction. Let's look at another example. Potassium hydroxide plus aluminum nitrate. Again, compound plus compound. I need to think double replacement. I personally like this method where I write the ions out and kind of circle the ones that go together so I can make sure I've got positive being attracted to negative. But if you just want to do straight replacement, you can do that. Just kind of swap the places of the aluminum with the potassium. So now I'm going to have aluminum with the hydroxide, and I'm going to have potassium with the nitrate. I just have to make sure that I'm writing the correct formulas. So I need to know that potassium has a charge of +1, hydroxide has a charge of -1, aluminum has a charge of +3, and nitrate has a charge of -1. So when I write aluminum with the hydroxide, I need 3 hydroxide ions. And potassium pairs up exactly with the nitrate. Potassium with the nitrate, the charges balance out. So these are the correct formulas, but I need to balance this equation. It's not balanced. I'm going to need 3 hydroxide ions to balance out my 3 hydroxide ions here. And I need and then that is balanced once I write a 3 over here, so I have 3 potassiums and 3 nitrates. Just one more type of reaction, and this is combustion. I alluded to this earlier. Combustion is a little more complicated, in part because there are 2 versions of combustion. Combustion is just a fancy word for burning. It describes a substance reacting with oxygen in a way that releases a large amount of heat and light. So rusting is also combining with oxygen, but it doesn't release a large amount of heat and light. Not everything that involves oxygen is combustion. But there are two main types of combustion reactions. Type 1 is actually just a super hot and bright synthesis reaction. So oxygen is an element. So if it reacts with another element in such a way that it burns, then this is a synthesis combustion reaction. And just like the synthesis reaction, it has the same general form. A plus B makes AB. An example of this would be burning magnesium ribbon. Burning solid magnesium burns with a very bright white light to produce magnesium oxide. We don't normally write down the heat and light, but if it's included, it's because somebody wants to draw your attention to the fact that this is a combustion reaction, not just something like rusting that just happens with oxygen. The type that needs a bit more discussion, because we haven't talked about it yet, is the combustion of hydrocarbons. Hydrocarbon, as the name implies, contains hydrogen and carbon. Sometimes they also contain oxygen as well, and when those compounds combust with oxygen, they form carbon dioxide and water. So those are the products. And an example of this would be carbon tetrahydride gas reacting with oxygen to form carbon dioxide plus water. The products are always carbon dioxide plus water. That makes predicting the products of a combustion reaction very easy, so long as you can identify from the reactants that it is a combustion reaction. So let's look at how we do that. If the reactants are a hydrocarbon plus oxygen, then it is a combustion reaction. So here's my hydrocarbon and here's my oxygen. So this is a combustion reaction. The one thing to watch out for is that it almost looks like a single replacement reaction because I have a compound plus an element. And I told you when we talked about single replacement reactions that that was the format. So you just need to watch out. If you think it's single replacement, just make sure that the element isn't oxygen and that the compound isn't a hydrocarbon. But otherwise, the products are carbon dioxide and water, CO2 plus H2O, CO2 plus H2O. So those are the reactions. They're not balanced equations yet, and it's the balancing of these equations that sometimes gets tricky. To get 4 carbons over here, to get 10 hydrogens, I need a 5 here. Now I have 2 times 4 is 8, plus 5 is 13. So I want to have the number 6.5 here. Of course, that's not a correctly balanced equation. So I need to multiply everything times 2. 2, 13, 8, 10. That's correctly balanced now. All right, how about balancing this equation? We have 2 here. Notice that there are 6 hydrogens on the left, so I need 3 times 2 is 6. I have 2 times 2 is 4 oxygens plus 3 more oxygens is 7. How do I get 7 oxygens over here? There's already 1 oxygen here, so I just need 6 more. 3 times 2 is 6. And this is a correctly balanced chemical equation. This video took a bit of time because we had 5 types of reactions to talk about. So I'm going to split the practice problems into a separate video. But watching that video is super important because you need to know how to pick the right type of equation out when you don't know ahead of time what kind of reaction it is. So be sure to go to that one next. I hope this helped.